All right. So in this problem, now this is not a proof, right? We just want to sort of get our hands on how the definition works here. So we're looking at this curve. So this is y equals f of x equals x squared y x. And we're trying to consider how, we claim that the limit as x approaches 0 is equal to 0. So on the x-axis here, we're going to look at the point x equals to 0. And, of course, the point on the curve there is at y equals to 0, because we're asserting the limit's equal to 0. So we're sort of looking around this point. And in order to assert that limit actually is equal to 0, we've got to show that for every epsilon, there's a corresponding delta. Now, this problem just asks us just to consider one particular value of epsilon. This is not sufficient to prove anything, right? But let's just say, for example, that I do. So here is a little interval of radius epsilon around L. So L is equal to 0. And this is, of course, 1/2. And this is negative 1/2. Oh, gosh, that looks like a 1/2 again. Okay, so there we go, negative 1/2. Cool. So now I just want to know, well, what sort of an interval, can I pick? It specifically, the problem says, what's the largest value of delta? Now, clearly, you could use a super small value of delta. And generally speaking, given the choice, yeah, I mean, just to be safe, you might as well pick a small one, right? But here we want to pick the largest value of delta because the problem wants to make us demonstrate that we know what the rules are. And if we pick the largest acceptable value of delta, then we clearly know the rules. Does that make sense? Yeah. So, okay, well, what I need to happen is I need to make sure that all the values of the function end up falling in this range. So now I could pick a little neighborhood about yay so big, and sure enough, all those values of the function are in that range, but I could also make it a little bigger, etc. I could make it a little bigger. Eventually, though, if I try to make it this big, nope, that doesn't work. That's too big, because this point here, for example, the value of the function is not in this interval. So the cutoff, I think you can see, is going to be, and I'm just going to appeal to your geometric intuition here, your cutoff is going to happen like this. So I claim that this is our biggest interval. And I've just got to figure out, well, what are these points, and what does that mean that the corresponding delta is?
So you just plug in like a half.
Well, it's you got to be a little careful. But yeah, so the value that we're looking at, this endpoint of the interval that I'm looking at here, that number, when I square it, needs to give me a half.
Oh.
Right? So I'm going to make this, actually, I claim that this is the square root of a half. What about this number? Well, this number, when I square it, gives me a half also, but this one's the negative. So this is negative square root of a half. And notice that conveniently, that is a neighborhood centered at 0. And so I could just say, oh, well, then clearly, for this, epsilon equals to 1/2, my delta, I can just choose to be the square root of a half. Does that make sense? And I claim this is the largest possible value of delta. You pick any delta bigger than that, and you're going to have some points that fall outside of the interval, not allowed by the definition.
So epsilon is it always like the
epsilon is always
the output?
Epsilon is always what we call the radius of the interval around the output value, or around the alleged limit, the would-be limit. Yeah. Right. And then delta is always the radius around the point we're approaching. Does that make sense? Any questions about this problem? Okay, let me stop the recording.